Alright, so at the end of the last video, we were talking about how a nuclear reactor works. We had our control rod, or our fuel rods inside the core of the reactor. Around them were the moderators, the material which was slowing down the high-speed neutrons released from the fission reaction, turning them into thermal neutrons that could be reabsorbed by the uranium-235 and used to split more uranium-235 nuclei. Then we also had the control rods, which we raise and lower inside the core of the reactor to either speed up the rate of the reaction, or slow it down. If we lower the control rods all the way down, the reactor goes into shutdown. The moderators, the most common ones are water, heavy water, or graphite. The control rods, the two that usually are used are cadmium and boron. The control rods love neutrons. They absorb all the neutrons. When a reactor goes into shutdown, there's still some heat being generated, not the crazy amounts like there are when the fission reaction is actually going on. But even during shutdown, the coolant needs to flow. So the coolant is the material that moves in and out among the fuel rods and carries the heat away so that the core of the reactor doesn't go into meltdown. It carries that heat away and it uses it. It turns it into like electrical energy that we then use. Right at the end, I was talking to you about how the coolant still has to flow even when the reactor is in shutdown. Okay, because otherwise you could have a meltdown of the core, and if that happens, usually there's an explosion. And obviously Chernobyl would be the worst nuclear disaster. And I'm sure you've read about that. And that was like in the 80s, and people still can't go back there. Some people have, but they shouldn't, because the whole surrounding area is still so radioactive. And then right at the end, we were talking about the radioactive waste. So some of the radioactive waste, like the fuel rods, are highly radioactive, and their half-lives are like tens of thousands of years. So what do you do with them? So the most common thing that's done with them is that they are placed in a double-walled container in hopes of keeping the radiation in. And it's really pretty cool. They bring the double-walled container like right above where the fuel rod is, and then they use this machine to suck it up so that like it doesn't ever actually come out and get exposed to the air. So they put them in these double-walled containers, and then they bury them in isolated places like underground caves and in the middle of nowhere. Of course, we all know that what's the middle of nowhere now, in 15 years' time, might have a city on top of it. So that's some of the concern. So those are the things that are highly radioactive. Lower level radiation, sometimes it's held for a while until enough half-lives pass, and it's not as highly radioactive anymore. It's often diluted, and then they're released into the environment, unfortunately. Okay? So radioactive waste. The one last thing with reactors is the production of plutonium. So I had said to you that usually it's uranium-235 that is used, but more and more recently we've realized that if you take uranium-238, which isn't fissionable, but if you shoot a fast neutron at it, it will undergo beta decay and it'll become Neptunium-239, and then it undergoes beta decay and it becomes Plutonium-239, which is fissionable. And so more and more recently they're saying, hey, so these fuel rods of uranium-238, that are spent, like the 235 is already used up from them, could we then somehow turn them into plutonium and then use them? So reactors that do that, they're called breeder reactors, because they're breeding their own fuel. And then there would be, in theory at least, less nuclear waste. So it might be a way into the future. Another way into the future was one of the options that was on your nuclear projects that you were at one point going to do. And there are those mini reactors that are being looked at that are, in theory, supposed to have less waste, be less expensive. I'm saying in theory because there's still a whole truckload of controversy, of course, around them. All right. So that was fission. It is now time to talk about fusion, the fourth type of artificial transmutations, fusion reactions. Fission was splitting apart. Fusion is bringing together. Okay? So fusion is when you take two light nuclei, tiny little guys, and you put them together to form a heavier nucleus. Okay? The mass and the two light little guys, and when I'm saying light, I really do mean light, right? We're talking hydrogens. We're not talking like even carbons. We're talking tiny. So we're putting them together to form something that's slightly larger, but the binding energy will be less, right? Because these are tiny, they're still all tiny, you're going to save some in the binding energy here. And when that happens, then the difference is released as energy. So the mass of the nucleus formed is less than the mass of the two nuclei in the reactants, and the difference in energy then is converted. The difference in mass is converted into energy. For fusion, the energy that's given off is more per nucleon than fission. Okay, so this is actually per nucleon. Fusion reactions give off more energy. But there are problems. It's not easy to get these two hydrogens together. Okay, so we need to have very high kinetic energies. They need to have very high kinetic energies to overcome the force of repulsion that would be between them. And that can only be achieved at really high temperatures. And I'm saying like really high temperatures, like 10 to the 8th Kelvin. We're not just talking like 200 degrees Celsius, 10 to the 8th Kelvin. And it has to be maintained for more than 1 second, which is not easy. And the fuel has to be really dense. It is not easy to get these conditions, okay? To have that high of temperature held for that long of a period of time, and that the fuel be really dense. And because it's not easy to get those, we actually have not been able to do a controlled fusion reaction, right, in a lab. Fusion reactions happen. They happen in the sun and in stars. They've happened in the hydrogen bomb, but they haven't happened in a lab. We have not yet been able to control a fusion reaction. In a hydrogen bomb, the way we reach that high of a temperature is we cheat and we use a fission reaction first. So one part of the hydrogen bomb has a little uranium-235 in it, and when it explodes, it compresses the fuel and raises the temperature, and then it can undergo fusion. Okay? But as of yet, we have not been able to do this in a lab. There's tons of money being poured into it, and that's because we would rather use fusion than fission. We would rather use fusion than fission, one, because more energy per nucleon. Two, look at the reactants. The reactants are easily obtainable. We have to mine uranium-238, 235, but these are all hydrogens and isotopes, so they're much more attainable. And look at the products. They're not highly radioactive the way they are in in fission. So we would much rather use fusion, but we don't, simply because we have yet to be able to control it. Okay? So fusion would be better. Reactants are easily obtainable. Their products are not nearly highly radioactive, and you get more energy per nucleon. But we have yet to be able to get this high a temperature, a very dense fuel for that period of time. Problem.